Hi, so today I got a problem on the board. I'm working on factoring a cubic, and specifically, I want to work on factoring this using Vieta's formula. So there may be, and I'm not saying that Vieta's formula is the best way to do it. You may have better results using, I don't know, using other methods, particularly using, I'm spacing on the name of the method right now. Right off the bat. What am I thinking of? The rational root theorem. Yeah, so the rational root theorem is probably usually the faster way. You can, but for this video I'm just going to focus on Vieta's formula, and then I can possibly do a similar video on the rational root theorem at another time. So what I want to do, um, let's see if I have in the help. Do I have Vieta's formula in here? That's pretty weak. So Vieta's formula gives us a nice way of finding the sum of the roots in different forms. So what I'm going to do for any, and it works for any size polynomial. So it's maybe most commonly used on a quadratic, but like any polynomial can use this. So what it does is you can find the sum of all the roots. So we're calling the roots A, B, and C. Or you can find, well, you usually want to do all these, but the sum of the products of two roots, and then also just the product of all the roots. So all three roots being A, B, and C. So it doesn't, you could have a huge polynomial. It would get it when you have a huge polynomial, like if this was like degree 8, it gets real messy because then you got 8 variables. And but you could still have the same result where you could still find the sum of the roots one at a time, two at a time, and up to the product of all the roots, regardless of how big the polynomial is. Okay, good. So then the next thing it says is we can get these three values from the polynomial just using the coefficients. So then let me just kind of, and what you do is you always, so the sum of all the roots is always going to be the lead coefficient and the second one. So it's always going to be, and it's always going to be negative. So like negative 10 over 3. So for example, if you had, so the most common, you had like, when you have a quadratic, the sum of the two roots, if we say the two roots are alpha and beta, then that sum is going to be just minus b over a. But this works for any size polynomial again, so we're using that on the cubic. And then next, let's go back to blue. So next, the sum of the product of roots 2 at a time is going to be just, you just go to the next term, and the signs alternate. So this is going to be negative 1 over 3. So we're just taking everything is going to be like if this is, I don't want to use a because I'm already using a. Shoot. So let's just say it's in this form. So then we're gonna like, we're basically saying the sum of the roots is gonna be minus n over m. Next one's gonna be p over m because we're interchanging signs. Next one's gonna be minus q over m, and so on. So hopefully that clears it up a little bit. I don't know, maybe I should have just introduced Vietas a little better. I'll try to do better next time. So so then finally for our product of the product of the roots is going to be, go back to blue, minus 12 over 3, but we want to switch up the sign, so that's going to be a positive. And I actually don't want to reduce this because I'm going to show you why in a second. But so basically we're just doing like a ratio of the coefficients. Another thing people often do, if it's nice if you divide out and you have just a one, if this was just a one for the first term, then everything becomes integers. But we don't have that in this case. And if I divide, it's not a common factor, so it's not gonna divide nicely. Okay, and then the next thing I want to do, so yes, we could reduce this to 4, but I don't want to do that because we're not going to be able to reduce all of them, as obviously 1/3 is already reduced and 10/3 is already reduced. So what I'm going to do is just going to define something here. I'm going to create a new set of variables. So I'm going to say A is going to be 3 times little a, and B is going to be 3 times little b, and big C is going to be 3 times little c. And then what we can do is we can just update our roots. Like, I'll write the first one out. So we write this out like this. This is just going to be -10. Because all we've done is actually multiplied both sides here by 3. Okay, so that's going to be -10. So what I'm really saying, I'm going to kind of get rid of this. What I really want is to say A plus B plus C equals -10. And then we're going to have AB plus BC plus AC is going to be -3. So notice in that one, I'm actually multiplying through by 9 to get -3. And the reason is because we get 2 terms. So in order to have, like if we have 3A times 3B, that's the same as 9AB. So that will be our second equation. And then the third one, we're going to multiply by 27. We're going to have the product of the roots. So we're going to have A, B, C. 27 is 3 cubed. So I'm really just doing 3A times 3B times 3C is 27 times this, which is going to be 108, I believe. Yes. Okay. So then we're not really interested in that. So now all I want to do is solve for the big A, B, and C. And so all we really have to focus on is these 3 equations. And all we're really going to do is try to solve for A, B, and C using what we have. And then the first thing I like to do now is I just want to factor, I want the prime factors of 108. So let's see, what's that, like 9 times 12? I'm just going to kind of do like a little scratch work because off the top of my head, I can't think about it, but let's see. So 108 is 9 times 12, and that's going to be 3 squared times 3 times 2 squared. And so what we're going to have is 3 to the third, 2 squared. Okay. Then for the next piece, what I want to do, so in some cases you can kind of like guess and check, but it can be kind of tricky. And one thing I like to think about at this point is like the signs. So you notice you have some negative signs, which tells me at least one of these numbers, A, B, and C, is going to be negative. But because A times B times C is positive, we actually know that exactly 2 of them are going to be negative, right? Because you can't, if all 3 were negative, then 108 would be negative. So 2 of these are going to be negative, 1 is going to be positive. And I'm not going to do anything with that right now, but I'm going to come back to that. So I don't know, maybe I'll make a little note here. We'll just say 2 are negative, 1 is positive. Then the next thing I want to do I need something a little better to work with. So what I always do, and this works pretty nice, is I take A plus B plus C and I'm going to square it. And I won't bore you with the details, but what you get is this. You can multiply this out or remember the formula, but it's just going to be this. And then we know what A plus B plus C is. It's negative 10. So if we square it, we get 100. That's kind of a weird little thing I did there, but I'm saying this whole business equals 100. And then what I want to use is this piece. I want to solve for A squared, B squared, C squared. So let me write it out like this. We want A squared plus B squared plus C squared. So I'll do is subtract this piece from both sides. So I'm going to subtract this, but I'm going to substitute in. We already know this value because we have it right here. That value is negative 3. Then just doing a little simplification, what we can say is that A squared plus B squared plus C squared equals 106. Okay. Then at this point, all I do, this is really why I got these prime factors here. I'm going to do a little process here. So all we want to do, we know what all of our factors are. We have this prime factorization, and we know that we just know that we have to arrange this some way to get, when we add them, it's going to be negative 10. And I'm not worried about signs at this point, right? Because some of these are negative and some are positive, but I'm not worried about that right now. And I'm not really going to use this guy, this middle equation right now, because it's I just find that a little harder to deal with. So what I'm going to do, that's that the convenient thing with this equation, our square, having everything squared, is we really don't have to worry about the signs because everything's going to be positive when you square it. So I just like systematically, what I do is I look at what squares are going to give me something less than 106, right? I can't, and so like for example, I can't use 11 because if one of these values, A plus B, A, B, or C, sorry, is 11, we're at 121, we're over. So we're looking at a max of 10. And what I'm going to do, this is a little excessive, but I'm going to just, okay, write out all the factors that I have to use like this, right? And then I'm looking, okay, I can't really get a 10 out of this, but I can get a 9. I just, and you don't have to do it this way. This is just like my like little method of going through the numbers so that I don't miss anything. So, just maybe you can find your own way, but just the way I like to do it. So, and we don't have a 10, we don't have a 5, so there's no way to get a 10, but 3 times 3 is 9. So what I'll do is we'll start with our 106, and I'm going to subtract off 9 squared. 9 squared is 81, and we're left with 25. Yeah, we're left with 25. What I'm just going to do is I'm going to cross those off as I use them. Then kind of look for like the next biggest number. I kind of just repeat the process, right? So, okay, like 6 squared, but 6 squared is going to be too big because I can only go to 25. So I'm going over at 6. We don't want that. So I could try 4. So bring this down. 25 minus 4 squared. And 4 squared 16 minus 25, and that's going to give us a 9. We'll cross those off. And then we're left with, we just have this 3 left over, but that's going to be good because 9 minus 3 squared equals 0. So I find this tends to like get to sometimes you have to try a couple things, right? Because it's not always going to work, but by this method, you get pretty quickly to the actual roots that you're looking for. Okay, so what we have as our possible roots, plus or minus 9, plus or minus 4, right? Because we don't know the signs yet. But we do know, we know 2 are negative, 1 is positive. And what I'm going to do is I want to use this equation here. So let's just see. I'm saying a plus, let's get some color in here. A plus b plus c equals -10. And we have two negative numbers and two positive numbers. Just kind of, I just trial and error. So like, let's see, I think 9 and 4 is 13 minus 3. So like, let's see if I did -9 minus 4 plus 3 equals -10. Just trial and error. And yeah, that's going to work. And then I like to kind of just like double check a little bit, right? Like if you think about if you multiply this out, 9 times 4 is 36 times 3 is 108. And then if you really want to get, um, you really want to check it out, you can multiply well, multiply each of them like so. -9 times -4. I don't know. We'll do this real quick. -9 times -4 is 36. -4 times 3 is -12. 3 times -9 is -27. That's -39. 36 minus 39 is -3. So that kind of excessive, but that checks that all everything works. Okay, so we found our roots A, B, and C, but we only found our roots for capital A, capital B, and capital C. And so we have to, whoops, whoa. Oh, wow, there's other stuff over there. Don't look at that. Okay, didn't realize I had other stuff on this board. But we have to go back and we have to substitute again because we have our original definition of A, B, and C. So let's just take care of that. So let's see, let's get rid of this. So we're saying like A equals -9, but A equals 3A. So if we just divide both sides by 3, we can get our little a. So little a is going to be -3. These are all going to be the same. We're going to divide by 3 in each case. So if b is -4, then we divide by 3 and we get -4/3. And if c is 3, our little c is going to be 1. And then the question here, we're not looking for the roots, we're actually looking for a factorization. So the way to put that just real easy in that form is you keep the leading coefficient and then you just kind of write out the roots, just changing the sign, right? Like so for -3 to be a root here, we say x plus 3. You just reverse the sign. X plus 4/3. So 4/3 is a root. And x minus 1, because 1 is a root. And then I just like to, you don't have to do this, but like to distribute just to get rid of any fractions. So for the final answer, we're going to have x plus 3 times 3x plus 4 times x minus 1. Let's just check the answer over here in the quiz. So this one. That's correct. So that's all. It's like you see, that is actually a pretty long process. So it's like I'm not telling you it's fast or it's easy or anything. It's just interesting to have good practice to use Vietas, and it's like I think it's good to like know how to use Vietas, but it's not necessarily the fastest. So what I'll do, I'll put a link to this quiz in the description of the video, so you can. There's an infinite number of these. That'd be a question for another video, is when you have random quizzes like this, is it really infinite? No, it's not infinite because there's like the coefficients here are within a certain range, so it's probably only like maybe like 1,000. There's like 1,000 problems in here, maybe. Maybe a little more than that. I don't know. So yeah, I'll provide a description. I'll provide a description. Yeah, I'll definitely provide a description, and there'll be a link in the description You can practice these quizzes. And then also, I think, yeah, I think I will do, I think I want to do this using the rational root theorem just to see how much faster it is or what problems I might run into. So I think I'll do that next.